Integration and analysis. My name is Sondolo Afemi Bodogbe, PhD student in Mathematical Sciences at Indiana University, Indianapolis. So far so good. We have covered chapter 1 of this textbook we are using now. We are now in chapter 2, and then in our previous videos we have checked the outer measure. But one of the properties that the outer measure failed is the countable additivity. We see that the outer measure is not equals to A plus B. Okay, and that is one of the things we are trying to handle by getting another notation called mu, and can we actually extend it whereby it's going to satisfy all the properties of outer measure we have checked in our previous videos. So if you have not watched the previous videos, I will urge you to watch the previous videos so that you can flow within this section 2b. So before we go straight to measurable spaces and then functions, so let's first of all get some basic ideas by trying to check if we can actually find a notation length of all subset of R that will satisfy the necessary properties that we want. So the first thing we are going to check is non-existence of extension of length to all subset of R. Okay, so we want to consider that there does not exist a function mu with the following properties. So A, mu is a function from the set of subset of R to 0, infinity. B, the measure of I is equal to the length of I for every open interval in R. C, the length of the countable union of set AK is equals to K equals to 1 to infinity, measure of AK, which is called countable additivity for every disjoint sequence A3 of subset of R. And then D, we have translate invariant is equal to measure of A for every set A subset of R and every T that belongs to R. So we tried to show that there does not exist a function mu that satisfies all these 4 conditions. So let's prove. Suppose there exists a function mu with all the properties in the statement of the result. So let's check, observe that the measure of empty set will be equals to 0, and this follows from B, or because the length of an empty set is 0. So then we have that. Another thing is if A is subset of B and A is subset of R, then the function B of this is less than function mu B, and this as follows from condition C, which is countable additivity. The reason is because we can write B as the union of the disjoint sequence A, B, take away A, empty set, dot. And thus the measurement of B equals to mu A plus mu B, take away A plus mu empty set, dot, and this equals to mu A plus A plus mu B, take away A, and obviously these two guys is greater than mu A, because mu B take away A is greater than or equals to 76, then the addition of that will be greater than this. So that makes sense. So we also have if A, B are elements of R with A less than B, then based on what we have proved in previous video, that this is a subset. The open interval is a subset of a closed interval, and for small external greater than 0, this is also a subset of this, A minus external plus A plus epsilon for every external greater than 0. So thus B minus A, which is the length, will be less than mu of A, B, right, and this is less than B minus A plus 2 epsilon for every epsilon greater than 0. So hence, since epsilon is arbitrary and mu B is between, then we have this to be equals to B minus A, and that also satisfies the outer measure. The outer measure of a closed bounded set is equals to the difference of their length. Okay, so now we want to go to the last condition, which is if A is a sequence of R, subset of R, then we can actually add this guy as a disjoint. We have A1, A2, take away A1, A3, take away A1, union A2. So you can continue like that. So the measure of the entire countable union of these, because of the measure of A, since they are disjoint, they're not overlapping, you have A to take away A1. So you have mu A3, take away A union A2, dot. So by countable subadditivity, you know that this is less than or equals to summation AK mu AK k equals to 1 to infinity. So that actually follow from the countable additivity. So this has actually shown that mu has the property of outer measure that we used in our previous chapter, section 2a. So, but we realized that the measure of A union B is not equals to mu A plus mu B, which is the good challenge that we are trying to see how we can actually do it. So we see that there is not any properties of mu that satisfy all these conditions. Okay, especially this section C. So you are unable to get this section C. So that will lead us to get is there a way we can actually get all these properties, because all these properties are actually necessary for us to able to find the area under a function successfully. So and then we cannot remove any of these properties. We cannot remove property B. We should be able to find the length of an interval, open interval. Then we cannot remove this because we are actually in this point in order to show the limit of a sequence of a function. And then the translation invariant is very, very important, or else it does not make any sense. So what we just need to do now is that we want to see whereby we can relax these properties A, whereby it will not be the subset of the entire R. And for us to do that, we need what is called σ-Algebra. So here comes σ-Algebra definition. Σ-Algebra. So it says, suppose we have X is a set and we have fancy X, or call it X is a set of subsets, of X. Then fancy X is called a σ-Algebra on X if the following conditions three conditions are satisfied. So first we have empty set is in the σ-Algebra. Our σ-Algebra is also closed under complement. Then it's also closed under countable union. So if E1, E2, dot is a sequence of elements in X, of X, then their union also should be in our σ-Algebra. So that is the basic properties that a σ-Algebra must satisfied. Let's take some example. Suppose X is a set, which we can call the universal set. Then empty set and X is a sigma algebra on X. Because it actually satisfies these three properties, which you can verify. It contains the empty set, and the complement of the empty set is X, so it's closed on that complement. Then the union of this is X, which is also belongs to X. So this actually satisfies those three properties. So in topology, we call this kind of in discrete topological space, but here are dealing with in analysis. So suppose X is a set, then clearly the set of all subsets or subset of X is a sigma algebra on X. That is, if we take the power set of all sigma algebra, and the result also will be sigma algebra. Another example that you want to take note of is suppose X is a set, then the set of all subsets E of X such that E is countable or its complement is countable. Its complement is countable. So it's a sigma algebra on X. Example is a rational number. Okay, so you can actually verify that. So another good properties that our sigma algebra satisfied is sigma algebras are closed under countable intersection. So we list this and then define. So suppose S is a sigma algebra and a set X, then 1 X belongs to X. That is obvious. And if D comma A belongs to sigma algebra, then their union also must belong to sigma algebra, and get their intersection. Careful now. Okay, then their intersection also must belong to sigma algebra. Then thirdly, if we have a sequence of E that belongs to sigma algebra, then their intersection also countable intersection is also belong to sigma algebra. So let's start with the first one. So proof. Don't forget, if X is a sigma algebra, then it must contain empty set. And if empty set is in sigma algebra, then x, then empty set take away, then x will be equals to x take away empty set. So this also belongs to sigma algebra, since sigma algebra is closed under countable, is closed under complement rather. And I prove the first case because X is sigma algebra, and part of the property of sigma algebra is that it contains the empty set. So if it contains the empty set and then is sigma algebra, then the complement of the empty set also must belong to X, and that is X. That shows that X belongs to sigma algebra. So this third properties. Let me highlight it, then take it down. So B so proof. So if D, E belong to sigma algebra, and since sigma algebra is closed under countable union, then the union of these two should belong to sigma algebra. So we are done with one part of it. So this, we are done with this part. So this part is by De Morgan's law. X take away the intersection E is equals to X take away D union X take away E. Okay, so since D belongs to sigma algebra, then the complement of this belongs to sigma algebra, and since E belongs to sigma algebra and sigma algebra is closed under complement, then this whole part belongs to sigma algebra. So then those, so take my pen, so X take D common X take E elements of X. So their union also belongs to sigma algebra. Why? Because sigma algebra is closed under countable union. So that means that those the right hand, the left hand side is an element in sigma algebra. Why? Because that is just the complement of X, and X belongs to sigma algebra, then that conditions holds. So in other words, the intersection E is in sigma algebra. So the third properties, which I'm going to highlight now. So the third properties, so by De Morgan's law, so X take away n k equals to 1 to infinity ek is equals to union k equals to 1 to infinity with X take away ek. So since for each k, AK is an element of σ-Algebra, then the complement also element of σ-Algebra, since σ-Algebra is closed under complement, thus UK equals to 1 to infinity. Let's take away AK belong to σ-Algebra, since σ-Algebra is closed under countable union. And that completes our proof. Okay, you can take your time and go through it again. So from there now we can now define what is called measurable space and measurable set. Definition: measurable space and measurable set. So definition: a measurable space is an order paired. We have X and then σ-Algebra, where X is a set and fancy X is a σ-Algebra on X. Okay, now we have measurable set. So an element of σ-Algebra is called an X measurable set, or simply just call it just a measurable set if fancy S is clear from the context. So for example, now our DE are measurable set. So from there we can now move to Borel subset of R. But before we define what a Borel set is, let's take note of this theorem. The smallest σ-Algebra containing a collection of subsets So the theorem says, suppose X is a set and we have called the A is a set of subsets of X, then the intersection of all, then the intersection of all σ-Algebras and X that contain our fancy A is a σ-Algebra and X. So that is also an interesting question to check. So I'll just highlight the proof, then you can think over it on your own. Okay, note that there is at least one sigma algebra on X that contains A. So because sigma algebra contains the full set, right? Consisting of all subsets of X have to contain A. So we can now select X be the intersection of all sigma algebras on X that contain fancy A. Obviously, so once you check that this S, our goal is to show that this X is a sigma algebra, and we define it to be the intersection of all sigma algebra on X. So if it is intersection of all sigma algebra in X, then by definitions of intersection, each of the sigma algebra have to contain empty sets by the properties of empty sets. That means that automatically empty set will belong to X, because when you take the intersections of all sets that contain empty sets, then you are going to have empty set as part of the element. Okay, the next property that you need to show that if A belongs to sigma algebra, then X take away E also belongs to sigma algebra, which is enclosed under complement. So if A is in X, that if you can find E here, that means that there is E in all the sigma algebras which intersections we take. Okay, so and if E belongs to those sigma algebra and those sigma algebra are closed under complement, definitely X take away E will be in each of those sigma algebra that contain fancy A, and that means that S take away E also belongs to the sigma algebra. So the next thing is to check is that if E1, E2 belong to sigma algebra, then their union also belong to sigma algebra. So you can also verify this, that if E1, E2 belong to sigma algebra, that means that all these elements are also in the sigma algebras that contain A, and if they are in each of them, then the union of each of these sets also must belong to each of them, and that shows that the countable union of this also belongs to sigma algebra. You can also take your time and prove that, and that shows that X, which is the smallest for the intersection of all sigma algebras, is also a sigma algebra. That means that if you take intersections of all sigma algebras that contain a particular subset, a particular set which is a subset of X, the result also will be a sigma algebra. So we actually need this in order to define what a Borel set is. Okay, so let's give example of what sigma algebra is. I think we did that before. Yeah. Okay, then I give an example of smallest sigma algebra. Example, smallest sigma algebra. Number one, we suppose S is a set. And fancy A is the set of subsets of X that consists of exactly one element, that is A, shows that X belongs to a full set. Then the smallest sigma algebra on X containing our A in the set of all subsets E of X such that A is countable or its complement is countable. X take away E is countable. Another example, we have suppose we have our A to be 0, 1, 0, infinity. I want to build a smallest sigma algebra that contains this interval, and the smallest sigma algebras, so sigma algebra and R containing A is the empty set which it must contain, then the full set R, then each of those sets, then the complement of each of those sets, which is 1 to infinity, union is 0 to minus infinity. That's the intersection of this. So the intersection of this, or the other part will be minus infinity to that. Then I need to take the complement of these two guys, and that will be, or the union of those two guys, that will be 1, infinity. And lastly we have minus, the complement of this is minus infinity, 1. So that is the smallest sigma algebra on R that can contain our set A as we defined. So we can now define Borel set definition. Borel set. So the smallest sigma algebra on R containing all open subsets of R is called a collection of Borel subsets of R, or we call it Borel sigma algebra. Borel subset of R. Then an element of each element of the sigma algebra is called a Borel set. Alright, so example, of a Borel set on R. Borel set. Don't forget Borel sets are elements from Borel sigma algebra, just like we have measurable sets to be sets that belong to our X measurable sigma algebra, to belong to X sigma algebra. So first, every closed subset of R is a Borel set. Why? Because every closed set can be, because every closed subset of R is the complement of an open set. Of an open set, subset of R. For example, we have A comma B, and then that is just equals to R. That is just R. Take away, and then define the complement. We have minus infinity to A union B to infinity. Okay, so this is just the complement of R. So if R is in our Borel sigma algebra, then the complement, then the complement also should be there, but also each of these is in our Borel sigma algebra of R, because this is an open set, this is an open interval, it's in R, this is an open interval, it's in R, all of this is an open subset, they are in R, then the complement also must be in R. That shows that our closed interval also is in R. So another example, every countable subset of R, countable subset of R is a Borel set. Why? Because if B equals to single set this, then their union T equals to 1 to infinity. Then if we define B, if B equals to this, and which is a Borel set, why is it Borel set? Because Sk for each k, Sk is a closed set, a single set is a closed set, then the countable union of their complement will give us an open set, open interval, and that means that the countable union of Sk also will be a Borel set, will be one of the elements in a Borel sigma algebra. So also every half interval, every half open interval A comma B, here A comma B belongs to R, is a Borel set. So the reason why this Borel set is because it is half closed. This half closed can be written as intersection, countable intersection of an open interval. Since this is an open interval, an open interval is a Borel set, and Borel sigma algebra is closed under countable, is closed under countable intersections. Then when we take the intersection of all this, then that also should belong to sigma algebra. Alright, last example. If f a function from R to R is a function, then the set of points at which f is continuous is the intersection of a sequence of open set, and that is a Borel set. So you can also verify that. So here we are going to stop for this video. In the next video we can now go to what a measurable function is. So here we are able to define what a measurable set is. First, a measurable set is an element of a sigma algebra, and then in Borel sigma algebra we talk about Borel set. Borel set is also a measurable set. So we have two types of set: likely, then we have a measurable set which is an element of X sigma algebra. Then we have a Borel set which is a measurable set but it's an element from Borel sigma algebra. Hope to see you in the next video as we are going to consider what a measurable function is. Thank you.